Okay, so hi everyone. In this video, we're going to look into the technique of proving by using mathematical inductions. We have theorem 2.3.2 here, which is on the principle of mathematical inductions. So in this theorem, I'm going to highlight what are the meaning of when we want to apply the mathematical inductions. Okay, suppose that we have the statement and let's denote that statement by Pn. So Pn be a statement that is either true or false for each n belongs to natural numbers. Okay, so the point here is that when we want to use mathematical induction, usually our statement, the domain of our statement is for natural numbers. That means n belongs to the set of natural numbers. Okay, so the statement Pn here will be true for all n belongs to natural numbers, provided that we have the following two conditions. The first one, we have P1 is true. Okay, so why 1 here? Because our case again refer to natural, and the first number of the natural number is 1. That's why we need to show that the first case is true, which means P of 1 is true. And the second one, for each k belongs to natural, we have the implication statement here. If Pk is true, then Pk plus 1 is true. Okay, so we have the concept of universal quantifiers for each. Then we have the statement implication, if then statement. Okay, what does it mean here? What is the difference between the first one, point A, we have P of 1 and equals to 1. Point B here, we have for each K. So K here is referred to some numbers in that naturals. Okay, so it's like this. For example, if you want to refer K here, refer to n equals to 2, so that Pk plus 1 refer to the next term, which is n equals to 3. If your K here refer to n equals to 4, then Pk plus 1 means for the case of number 5. Right? So if we can prove that one, which means the first one just now we have already showed that the first case is true, then in general, Pk and Pk plus 1 here represent the case of the next numbers. Okay, which means if you means the k is equals to 2, the case of k equals to 3 will also true. If k is equals to 3, k plus 1 refer to the next term, which is terms number 4, so on and so forth. So in all the cases, by the principle of mathematical induction, we have shown that the statement Pn is true for all the cases of n belongs to naturals. Okay, so in applying the principle of mathematical inductions, basically we have two steps. Okay, so the first step, which is P1 just now, which is also known as the verifying condition. So this step is called the basis for the inductions, right? So basis here also, you can say this is actually the first case, okay? The first case of our n. If n here belongs to natural, that means starting number must be 1. If let's say we want to check for the case of n greater than or equals to 2. So what will be the first case here? So the first case or the basis case here is n equals to 2. Okay, so that is the first one, basis for induction. The next one, step B here, this is known as the induction step. Okay, so we have that two steps in the principle of mathematical induction. We have the basis for induction, which refer to the first case, and we have the induction step, which contains the statement involving implication. If P, then Q. If PK is true, then PK plus 1 is true. Okay, so the assumption that PK is true in verifying part B is known as the induction hypothesis. Okay, because if you look into this statement, if P then Q, this is actually our antecedent, or sometimes we call it as the hypothesis. So we call it as the induction hypothesis. Right. So that's all for this video. So in the next video, we are going to look example how we are going to apply the principle of mathematical induction in order to do proving. All right. So thank you so much.